good morning. I'm Manohar Paluri from Facebook AI Research, and this is joint work by Emily Denton, Jason Weston, myself, Lubomir Bourdev, and Rob Fergus. In this work, we are going to try and predict hashtags given an image by modeling users along with the images. So I don't know how many of you use social networks or actually use hashtags when you use them. So just to go over the basics, a hashtag is basically a single word abbreviation, or in some cases multiple words by removing the spaces and concatenating them prefixed with a hashtag. And these are usually used by many people on social networks. So when you upload images, you also kind of give your version of what you want to tag in the images. So the reason we care about hashtag prediction is they go beyond concepts in the image, like objects or scenes or basically actions. So for example, they could be precise labels, like what is in the image. They could be about emotions and feelings. So it's not necessarily apparent in the image, but you are basically associating an emotion with that photo. They could be basically referring to currently ongoing events, or events that happened in the past, or that will happen in the future, or reoccurring events. And finally, they could be about really abstract ideas that are very specific to user in some cases. So basically what I want to say is these hashtags encapsulate a lot more information than just precise labels that occur in the image. That's why we care about predicting them. So just to give you a sense of certain examples that users have uploaded images to Facebook and what kind of hashtags they use. Here you see 3 images, and these are some concepts, some hashtags that they have tagged with. And pretty much these are aligned with what are in the images. But then these are some more examples where the hashtags that are used are pretty crazy. So for example, in the bottom left, the person probably had a really bad haircut when they were trying to do the haircut on their own, and it says not even mad. So it's very abstract basically. And in the last one, this person probably wrote some algorithm on the board and doesn't have much confidence. So it's like good luck algorithm. So it's really very abstract. So that's kind of the examples that we are dealing with at Facebook. So just to define the task again, our task is to predict the hashtags given the image content and the user information. To motivate why we want to use the user information along with the images, here are 2 example images that are uploaded to our network. And on the left is an image uploaded by a female residing in Canada who is 40 years old, and on the right is an image uploaded by a user in California who is 19 years old. And these are the hashtags that have been used. So the point here is, even though these 2 images are visually very similar, the hashtags that are used are very different. So for example, on the left one, this person probably doesn't experience so many sunny days in Canada. So they're basically saying fun in the sun or a beach day. They're specifically signifying that it's a good weather day. But on the right, this person is probably used to a lot of sun because she's in California. So she's basically saying, I'm doing surfing activity or growing up in California and so on. So the motivation here is we should be using not only the image content, but the information about the user to try and predict the hashtags. So our data set is 20 million images, and these are coming from 9.5 million users. And just to give you an idea again of the top hashtags that are in this data set is, I do not know how many of you people know the jargon. TBT is Throwback Thursday or Women Crush Wednesday, or there are these frequently used hashtags that sometimes might not be about the image at all actually. And the metadata that we use for these users is the age of the user. And since Facebook and the social networks cannot be used for users less than 13, so we go from 13 to 114, who is the oldest user right now on Facebook. And the gender. So some users in Facebook do not specify the gender. So we have 3 possibilities: male, female, and unknown. And we also use their hometown. Just to note, the location is of the user. This is not with respect to an image. Since we are doing user modeling, so the home city or the GPS coordinates is of the user. And in this study, we only consider English. So we limited our study to users from these 5 countries who are English-speaking countries. I want to set the notation so that we understand the next few slides. So we will basically use small y, which is basically an index to the dictionary of possible hashtags that we are trying to predict. We will represent the images with small x, which is an image descriptor, and we'll use an off-the-shelf convolutional network, which is now pretty much what everybody do in computer vision. And what we are trying to do in this work is learn two embedding functions. So we learn the image embedding function, and which is phi I of x. So given an image descriptor x, this embedding function is going to project that descriptor into a common embedding space. And phi h of y is the embedding function that we learn for hashtag embedding. So given a hashtag, we use that function to project it into the same embedding space. Now that hashtags and images are in the same embedding space, all you need to do is get nearest neighbors, and given a new image, you can quickly predict the top hashtags according to the simple dot product. So in this study, we basically simplify the hashtag embedding model. So we use a simple linear embedding for the hashtag. In this case, V is the matrix that you learn. So given a hashtag descriptor, we use the linear mapping and get the embedding vector for the hashtags. For the image embedding models, we do three various models. The simplest is the bilinear model, where we do not use any user metadata. So this is just using image data to predict the hashtags. And then the next one is the user-biased bilinear model, where we concatenate the image embedding with the user embedding. So in some sense, you're giving you are concatenating the two descriptors to find the nearest hashtags. And then there is the third model, which is much more complex, which is the three-way multiplicative model. So you get the image embedding function. So given a user descriptor, the image embedding function changes according to the user metadata. Those are the three. And I want to go into a little bit of detail into the three. So to give you a visual feel of how the system is. And given an input image, like I said, we use a convolutional network to get the feature descriptor. And this is very off-the-shelf convolutional network. There's nothing special here. And given that image descriptor, now we want to learn the embedding matrix P that will project the image into this common embedding space. On the right side, we have the matrix V that we learn that embeds the hashtags into the same space. And like I said, now that everything is in the same space, you can basically just do a nearest neighbor lookup, and that will give you the top hashtags that you can predict given a new image. This is the bilinear model, where we do not use any user metadata. In case of the user-biased bilinear model, what we do is, along with the image descriptor projected through P, you get an image descriptor, image embedding, and then you also learn matrix Q, which embeds the user metadata, and you concatenate the two. And now you have a space where you have both this descriptor, part of it is about the image, and part of it is about the user. So that is how you are able to do nearest neighbors using both image and user metadata. This is a more capacity model. So here we have a three-way tensor that you learn. So the basic idea, and you can read the paper for more details, but I want to give you a very basic idea. Here what we do is we learn a three-way tensor. So think of this three-way tensor as given certain user metadata, you take a slice out of the three-way tensor, and you use that as an embedding function. So you jointly learn this three-way tensor to basically, that incorporates user metadata, image descriptor, and the embedding descriptor. To go into a little bit more detail, the three-way tensor Z has dimensions small m, which is the user metadata dimension, capital D, which is the embedding space dimension, and small d, which is the image descriptor dimension. And the given certain user information, UI, you basically take the slice from ZI that will become your embedding matrix PU. So previously, in the simpler models, we had a fixed P. Now we have PU. So given certain U, you get a slice from this three-way tensor. And that is the embedding function that you learn. In reality, when you try, Z has MDD parameters, which is very huge and impractical to learn. So we constrain Z to be a low-rank factorist of this low-rank factorist form. So where alpha is basically a tensor that and K is something that you can experiment with, and alpha is the image embedding function that you learn, image embedding tensor, beta is the, alpha is the user embedding tensor, sorry, beta is the image embedding tensor, and gamma is the embedding tensor. And you basically take an outer product of these three to get Z. And Z has rank K brackets M plus D by D plus D, basically. So our training, we use the rank loss. This is a very common loss that is used when you're using a ranking problem, when you have a ranking problem. And it's also called weighted approximate rank pairwise loss, WARP. And this particular loss optimizes for precision at K. So the top K hashtags that you predict, that is basically what it is optimizing for. And you need to do negative sampling to train this loss. The big advantage of this loss is you can scale it to many hashtags. So in our case, the hashtag vocabulary is 10,000, but if your hashtag vocabulary was 100,000 or a million, you would still be able to use the same loss, and that is a good advantage of using ranking loss. It scales well to large hashtag vocabularies. Our data, so for each image, we have multiple hashtags, and for roughly 20 million images, we have close to 4.6 million distinct hashtags. So the important thing here is the hashtag distribution is very varied and heavy-tailed. So the top 10 hashtags itself basically accumulate to 4% of the total occurrences, and top 100 to 11%. So, and there are close to 4 million hashtags out of this 4.6 million that only occur less than 10 times throughout the data set. So it's very heavy-tailed distribution. And that is one of the reasons why we try to predict only the top 10,000 hashtags. One of the consequences of such a hashtag distribution data set is any measure that you have, error measure, will be heavily dominated by the top frequently occurring hashtags. So, for example, the common occurring hashtags like WCW, TBT, or MCM, which you can look into what they mean, have little to do with what is in the image. So it's really important to kind of train where those things don't affect your model. So we have two versions of our data set. And so the blue is the natural data set. So we basically take whatever the users have uploaded. And we make a balanced data set out of that, which is the red one. So what we do is for the top 500 hashtags, we randomly sample them such that they have the same frequency as the rest of the hashtags in the 10,000. So now we have two versions of the dataset, the natural dataset and the balanced dataset. We train models for both datasets, using both datasets. And I want to quickly point out certain things. So the frequency baseline is just predicting, which is the baseline, is just predicting the most frequently occurring hashtags. So there are three measures that we that we consider in this work. Precision at 1 is basically the top predicting hashtag from the algorithm, is it in the ground truth? That's precision at 1. Recall at 10 is if you predict 10, how many of them are in the ground truth? And accuracy at 10 is basically indifferent to the number of hashtags that have been used when the user has uploaded the image. One few things that I want to point out is the three-way multiplier model outperforms in both cases, but it does a much better job in the balanced data set because, like I said, if you use a natural data set, then you have a lot of bias with these frequently occurring tags which are not related to the user or the image. And another thing is the problem itself is very hard. You have to predict out of the 10,000 tags which one. So the accuracies are obviously low, but if you look at it, the accuracies of the balanced distribution are even lower because the entropy is higher because all the hashtags can occur with the same frequency. Whereas the top one, you can basically keep predicting the top occurring ones and you do a good job. I want to give you a qualitative view into how the model works. So here are some images, and we use two models, and I'm showing you results of both models, basically. The one trained on the natural distribution and one trained on the balanced distribution. So a few things I want to point out. The one trained on the natural distribution basically predicts more commonly occurring tags like no filter or TBT, WCW again. But the one trained on the balanced distribution ignores those because every hashtag can occur with same frequency and keys in onto what is in the image, which is probably what we want. And here are a few more examples. Again, on the left, the natural distribution keys in on the frequently occurring hashtags, but on the balanced distribution one, it is keying in on what could be potentially in the image. And also, again, to show a quick example, in the first case, it was probably taken in San Diego by a user in San Diego, so there you get hashtag San Diego as one of the potential hashtags predicted. So we also do a probe analysis. So given an image, we basically fake the age and gender and see what kind of hashtags the models predict. This is to kind of see how well the model is using the user metadata. So as you can see, the hashtags that are predicted are very different. For females with smaller age, it's love or boyfriend, and for females with older age, it's love him, sisters, or basically a little different. And for males who are older, it's proud dad and blessed, which most likely younger people will not use. And this is another example where the same image, if we consider the user coming from Sydney, what would be the hashtags? And if we consider the user is coming from Toronto, what would be the hashtags? And clearly, it keys in on hashtags which are location dependent. And Sydney is usually more beach oriented. That's what we have observed. And Toronto is more CNN Tower and other things like that. So again, I want to stress that depending on the user metadata, the kind of hashtags that we predict change, which is exactly what we want. We also do a simple t-SNE on the user embedding that we learn to see how much how much in the embedding space of the users there is clustering, and we can kind of do label propagation. So here in this example, there are a lot of people who do not specify their gender on Facebook. So when we see the embedding of the user metadata, you can clearly see them cluster well. All the females are together, and all the males are together, and all the green dots, which are unknowns, you could potentially think they are females because they are nearer to other females. And then we can also do the same experiment on location. Again, we see New Zealand and Australia users closer in the space, and Canada and US closer. So some more insight onto the user metadata, the user embedding being useful. This is another interesting plot where we cluster them, where we use t-SNE on the age. And as you go radially outwards from the center, the age increases. So again, here, the user metadata is used really well by the model. That's why the clustering is very nice. That's pretty much it. And I'm happy to take questions. Thank you so much.
So we have about 2 minutes. Any questions?
So that's really interesting, and it's obviously a hard problem, but with those kind of accuracies, what are you going to do with this?
So this was more of an experimental direction, and we wanted to kind of see first-level experiments on how much user information helps. And right now, the plan is not to use it in any production or any system, but keep on iterating on it. So one of the objectives of Facebook AI research is to work on long-term problems. So this is one of the long-term problems, potentially. Yes.
Those gender information and also like age, etc., and used for the prediction. But as a Facebook user, I can actually put whatever information into it. So they're not really reliable. So how can we resolve this problem?
Yeah. So noise is definitely one concern. But given we have close to 9 million users, our estimates of noise are much lower. So and these models tend to be reasonably robust. But again, noise is one problem. And one study that we could do on right now is to see which of these are outliers. So the model could be saying you're old, but you might have specified your age is low, right? So you could kind of see it as a way to kind of find these outliers. But in general, noise is definitely one of the concerns.
Okay, so one last question from me is how do you generate new hashtags?
So right now, the hashtag dictionary is static. One of the future works is to kind of work on models where it could be, the learning could be online and learn new trends and use new hashtags. So right now, in this model, we do not worry about new hashtags.
Okay.